Hey everyone, welcome back to Rajiv Infotech channel. If you're new here, I'm Rajiv and today we've got another exciting and educational video for you. We're diving deep into carbon and its compounds today, focusing on some of the most important questions that you need to know. Whether you're studying for an exam or just love chemistry, this video will help you understand this crucial topic better.
Question number 1. An organic compound A on heating with concentrated H2SO4 forms a compound B which on the addition of 1 mole of hydrogen in presence of nickel forms a compound C. 1 mole of compound C on combustion forms 2 moles of CO2 and 3 moles of H2O. Identify the compounds. Answer. To identify the compounds A, B, and C, and write the chemical equations of the reactions involved, let's analyze the problem step by step. Step-by-step analysis. 1. Heating compound A with concentrated sulfuric acid. When an organic compound, like an alcohol, is heated with concentrated sulfuric acid, it typically undergoes a dehydration reaction to form an alkene, compound B. 2. Addition of 1 mole of hydrogen to compound B, in presence of nickel. Hydrogenation of an alkene, compound B, in the presence of a nickel catalyst forms an alkane, compound C. 3. Combustion of compound C. The combustion of compound C, an alkane, producing 2 moles of carbon dioxide and 3 moles of water suggests the empirical formula of the alkane. General combustion reaction, CXHY plus oxygen, gives carbon dioxide and water. Given, CXHY plus O2, gives 2 molecules of carbon dioxide and 3 molecules of water. This indicates that the compound must contain 2 carbon atoms and 6 hydrogen atoms, that is C2H6. Identification of compounds. Based on the given information and the analysis. Compound A. An alcohol that, upon dehydration, forms an alkene. Possible alcohol, ethanol. Compound B. An alkene formed from the dehydration of ethanol. Possible alkene, ethene. Compound C. An alkane formed from the hydrogenation of ethene. Possible alkane, ethane, CH3CH3. Chemical equations. 1. Dehydration of ethanol to form ethene. Ethanol, in the presence of concentrated sulfuric acid, gives ethene and water.
2. Hydrogenation of ethene to form ethane. Ethene plus hydrogen in the presence of nickel as a catalyst gives ethane. 3. Combustion of ethane. Ethane reacts with oxygen to give carbon dioxide. Summary of compounds. Compound A, ethanol. Compound B, ethene. Compound C, ethane. These identifications are supported by the given reactions and their stoichiometric relationships.
Question number 2. The same molecular formula can represent an aldehyde and a ketone, say C3H6O, write their structures and name them. State the relation between the two in the language of science. Answer. The molecular formula C3H6O can represent both an aldehyde and a ketone. These compounds are functional isomers, meaning they have the same molecular formula but different functional groups and structural arrangements. Structures and names. Aldehyde, propanol. Structure. The structure of propanol includes an aldehyde group, CHO, at the end of the carbon chain. Name, propanol or propionaldehyde. IUPAC name, propanol. Ketone, propanone. Structure. The structure of propanone includes a carbonyl group, C double bond O, within the carbon chain, specifically at the second carbon. Name, propanone, commonly known as acetone. IUPAC name, propanone. Relationship in the language of science. Functional isomers, propanol and propanone are functional isomers of each other. Functional isomers have the same molecular formula but differ in the type of functional group they contain and their connectivity. Aldehyde versus ketone. Aldehyde. In propanol, the carbonyl group, C double bond O, is located at the end of the carbon chain, making it an aldehyde. Aldehydes have the general structure RCHO, where R is a hydrocarbon group or hydrogen. Ketone. In propanone, the carbonyl group C double bond O is located within the carbon chain, making it a ketone. Ketones have the general structure COR-, where R and R- are hydrocarbon groups.
Detailed explanation. Propanol, CH3CH2CHO, structure. The molecule consists of a 3-carbon chain with the aldehyde group attached to the first carbon. Naming. The prefix, prop, indicates a 3-carbon chain, and the suffix, anal, denotes the presence of an aldehyde group.
Bonding. The carbonyl carbon is bonded to one hydrogen and one carbon, methyl group, CH3, resulting in the structure CH3CH2CHO.
Propanone, CH3COCH3. Structure. The molecule consists of a 3-carbon chain with a carbonyl group attached to the second carbon. Naming. The prefix prop indicates a 3-carbon chain, and the suffix 1 denotes the presence of a ketone group. Bonding. The carbonyl carbon is bonded to 2 carbon atoms, both methyl groups, CH3, resulting in the structure CH3COCH3. Summary. Propanol, an aldehyde with the structure CH3CH2CHO. Propanone, a ketone with the structure CH3COCH3. Relation. These compounds are functional isomers of each other, sharing the same molecular formula C3H6O but differing in the functional group and structure. Question number 3. Explain the hydrogenation reaction with examples.
Answer. Hydrogenation is a chemical reaction that involves the addition of hydrogen to another compound. This process is commonly used in organic chemistry to reduce or saturate organic compounds, especially alkenes, alkynes, and carbonyl compounds, such as aldehydes and ketones. Here, we will discuss the hydrogenation reaction in full detail, including its mechanism, conditions, applications, and significance. Hydrogenation reaction general definition. Hydrogenation is the addition of hydrogen to a molecule, typically in the presence of a catalyst. The most common hydrogenation reactions involve the conversion of unsaturated hydrocarbons, like alkenes and alkynes, to saturated hydrocarbons, alkanes. Mechanism of hydrogenation. The mechanism of hydrogenation typically involves the following steps. 1. Adsorption of hydrogen. Hydrogen gas, H, is adsorbed onto the surface of the catalyst, dissociating into individual hydrogen atoms. 2. Adsorption of substrate. The unsaturated substrate, for example, an alkene or alkyne, adsorbs onto the catalyst surface. 3. Hydrogen addition. The hydrogen atoms transfer from the catalyst surface to the substrate, saturating the carbon-carbon double or triple bonds. 4. Desorption. The hydrogenated product desorbs from the catalyst surface, regenerating the catalyst for further reactions.
Catalysts in hydrogenation. Common catalysts used in hydrogenation include transition metals such as nickel, palladium, platinum, iridium, and rhodium. These metals provide a surface for the hydrogenation reaction to occur. Heterogeneous catalysts. Catalysts in a different way solid than the reactants, typically gases or liquids. Examples include finely divided metals supported on inert materials like carbon or alumina. Homogeneous catalysts. Catalysts in the same phase as the reactants such as Wilkinson's catalyst, chlorotoluene triphenylphosphine I. Conditions for hydrogenation. Temperature hydrogenation reactions often require elevated temperatures to proceed at a practical rate, typically in the range of 5300 dC. Pressure increased. Hydrogen pressure ranging from 1 to several hundred atmospheres is used to enhance the rate of hydrogenation. Solvent reactions can be carried out in various solvents that can donate electron density to the catalyst, often enhance the reaction rate. Applications of hydrogenation. 1. Food industry. Hydrogenation of vegetable oils used to convert unsaturated fats to saturated fats, producing margarine and shortening. Partial hydrogenation can result in trans fats, which are associated with health. 2. Petroleum industry. Hydrocracking converts heavy hydrocarbons into lighter fractions like gasoline and diesel. 3. Pharmaceuticals. Reduction of functional groups. Hydrogenation is used to reduce ketones, aldehydes, and other functional groups to produce various pharmaceuticals. 4. Chemical industry. Production of bulk chemicals. Hydrogenation is used in the production of methanol from carbon monoxide and hydrogen, and in the production of ammonia via the Haber process. Example of hydrogenation reaction. In your screen, you can see the reaction between ethene and hydrogen in the presence of nickel as a catalyst. In this reaction, ethene and alkene reacts with hydrogen gas. A nickel catalyst facilitates the reaction. Ethane and alkane is produced as the product. Significance of hydrogenation. Saturation of unsaturated compounds converts alkenes and alkynes into alkanes, which are more stable. Industrial applications. Used extensively in the food, pharmaceutical and petrochemical industries to produce a variety of important products. Environmental impact. Hydrogenation can be used to reduce harmful unsaturated compounds in emissions and pollutants. In conclusion, hydrogenation is a fundamental and versatile reaction in organic chemistry and industrial processes, providing a means to reduce unsaturated compounds, stabilize products, and create valuable chemicals. We've covered a lot already, but there's so much more to learn about carbon and its compounds. If you found this video helpful, make sure to watch our next video where we'll continue exploring more advanced questions on this topic. The link to the next video is right here, so don't miss out. Before you go, if you enjoyed this video, please give it a thumbs up, leave a comment with your thoughts or any questions you have, share it with your friends who might find it useful, and don't forget to subscribe to our channel for more amazing content. Thanks for watching, and I'll see you in the next video. Happy studying.